Hello everyone. In the last class, we have seen that how we can write recursive functions and how a recursive function builds up as well as in the memory. We have seen certain examples of recursive functions in the last class and how a problem like finding a Fibonacci number, writing a factorial can be formulated using recursions, and we have seen an interesting problem of Tower of Hanoi also. But one thing we haven't touched upon is that recursion is a very fundamental tool of problem solving because it has inherent features of decomposing a big problem into smaller subproblems, just like humans think of approaching a problem. Today's class is we will going to dedicate how to solve problems using recursive techniques. So how can we, looking at a problem, how can we formulate using recursion, and what are the new handles that recursion provides us in order to make our solution more efficient? So today's lecture, we will see with a set of examples how recursion can be invoked to solve a problem efficiently. To give you a nice overview, if you remember that recursion is basically solving a problem using top-down approach. By top-down, I mean that you have 4 such conditions to follow. One is your base case. So base case means that at the bottommost layer, you should have problems whose solutions are known, or rather the solutions that you could find directly from the problem instances. For example, 0 factorial is 1 is a base case for that problem. So when you know the base case, then your job is to decompose or split the problem into smaller sub-instances. So we call those steps as decomposition. So given n instance or a number of inputs to the problem, how we can split the set of inputs and call subproblems using a recursive call. So the third step is, after decomposition of the input instance, how do we recursively call and solve the problem? So now after having the recursive calls getting completed, so each of the recursive calls will give you solutions of those subproblems. Then comes the recomposition phases, where we climb up this recursion tree from bottom towards the top by getting the solutions of each recursive call and then combining them finally to get the overall solution of the problem. For example, in Fibonacci number, to compute a Fibonacci number of n, we need solutions from Fibonacci number of n minus 1 and Fibonacci number of n minus 2. So those two recursive calls, when it returns, we get the solution and find the Fibonacci number of n. So this is the overall strategy by which we try to solve a problem efficiently. Now here, some interesting points to note is that depending on the way we can split a problem and depending on how we compose a problem, it will really matter that how efficiently we are solving that problem. And this combination of final results can be, we may need all of them to get it. So for example, in Fibonacci numbers, we need solutions from n minus 1 instance of Fibonacci and n minus 2 instance of Fibonacci, and then we add it. So it's a combination or the concatenation of both results and doing it. This recomposition may also have been an OR kind of a thing, that I need only one-sided branch to return me a value, and comparing both sided branch, I will decide upon to take one and not to take another one. So it is not the case that combining the recomposed solution from in the bottom up steps always need all the values to take into account. It need all the values to take into account, but it is not maybe the ANDing of all values are required. Sometimes it may require the ORing, that I may need either one of those from there. We will see examples to highlight such combines and splitting steps. Recall the sum of square example that we gave. So we want to have sum of set of numbers within a range, square of the set of numbers within a range. So we are given numbers m plus 1, m plus 2 up to n, and we need to sum m square, m plus 1 square, m plus 2 square up to n square. This is the problem. So if you remember, what we did is that we try to split it in the middle and try to get the same function call with the half elements and making the square of them, and try to get solutions from the rest half of the elements and take the square of them, and then try to add those two set of values or the squares that is returned to get the final solution. So here the base case would be that in this way of splitting, I may reach a situation where my number of elements in a particular set becomes only 1. When it will happen, so you split it in the middle, then you split it again in the middle, then you split it again in the middle. So when your m and n will equal, that means you have only one element there, you will just return the square value. So that is your base case. What is the decomposition step? I am splitting every time in the middle position. So my decomposition step is trying to find middle and then splitting over in terms of the middle position is my decomposition of the sub problems. So see, the initial problem has this many instances, but the decomposed problem we formulate consists of two parts, each having half number of instances than the original problem. Now I recursively call those two routines from the first part as well as the next part. Now when these individual functions recursively return me a value, I recompose those values, meaning I take those values and have an addition between them and return it to the overall function. So this is how we look upon a problem and try to find out the base cases, how we split the problem, and how we recursively call the subroutine to get the solution. Finally, we decompose and produce the overall result. So this is the essence of or the basic steps or approaches to solve any problem using recursion. Since we are also dealing with the recursion tree, you have already seen this tree, that this is a function called tree, or the recursion tree we will say, where the bottommost nodes are the base condition nodes. You see the m equal to n is always in the bottommost cases. So I need 10 square, this is 10 square is 100, I return that. 9 square 81, I return that. So the unfolding of this kind of a recursion tree is from top down, that is our decomposition step. Then getting the solutions and combining is by bottom up, which is our recomposition step. And here, as you can see, the solutions are taken from both of the function calls and then composed with the composition function is a plus. We compose, that means we add the results and produce the final value. Let us see some more little bit of interesting problems. Suppose you want to search an element from an unordered list of n elements. Suppose you are given a list L. This list is nothing but an array. You may consider it an array or a set of n elements you are given. So then you need to find the element x, whether it is present or not in those set of elements, and there are total n elements in that list. So if you try to think of using recursions to solve these problems, you may go it in this way, that what is your base case? Your base case could be if there is only one element in the list, then what you will do? You will just compare that element with x. If it matches, you will say found. If it does not match, you will say I do not find it. Now your decomposition is, I will just split the list arbitrarily into two parts. Please note here, I am trying to see here how the splitting will vary and try to analyze that whether there exists a good split so that my approach becomes efficient. That is the beauty of devising a problem formulation strategy using recursion and trying to see that what kind of splitting and combining process will give me a most efficient implementation if I write the program. So therefore, you split the list arbitrarily into two parts having n1 and n2 elements in each part, where both elements sum will become n. Then you try to recursively call the same routine with the first part of the list with n1 elements trying to find x. The second part of the list with n2 elements again trying to find x, you call the same routine. So these are sub problems which are of smaller number of instances where you are looking for x. Now your recomposition, this when it returns and give you the value of f1 and f2, which may be 1 for I found the element and 0 for not finding the element. So if I say that I find the element from the first half or the second half, I return as the element found, otherwise I return not found. Very simple to think that how human look at it. If you are given a large list, you will try to see a part. If it gets found from that part, good. Otherwise, you try to see the other part. If it gets found from that part, good. Otherwise, you do not find it. So you split it and you try to find the element from both parts. Either of them, if it returns as success, you return as success that the element is found. So that is the overall strategy that we try to see when we try to use recursion. Now we will see, does the split really matter? Suppose we split it in the middle or arbitrarily. Or let's say I split it in one side list is always 1 and the other side list is always n minus 1. Which is usually you do when you go for linearly searching one of the elements. When you go for linear search, how do? You compare the first element and try to see whether it matches with x and then try to return that element if it matches. Otherwise, you discard that and try to go for the same approach with the rest n minus 1 elements. This is indeed a recursion. And this follows from the same principle that we are discussing now. We are splitting with 1 and n minus 1. That is the only difference in the split. Even if you will see that if you split also in the middle or any arbitrary position, you try to take examples of let's say 7 elements, 8 elements and try to arbitrarily split. And see, you will exactly need n number of compare between your x and the elements in the list to find the appropriate element that you are trying to search. So therefore, here the type of split doesn't matter, and in fact, indeed, that's why the linear search is the best way you can write this. Even if you split in the middle and try to do some jugglery, it doesn't help a bit. But we will now see another example where it actually matters. Just look at this example for the time being. Before that, let us try to see another example just in line with the search element, that how do we find maximum of n elements from a list L. So, given a set of n elements, again if my element is 1, I will just return that element as the maximum, because if the list has only one element, I have nothing to do. So that is my base case. Again, in generic sense, I will try to see how I could decompose and recompose. So let me arbitrarily split the list into two parts of n1 and n2 elements. Recursively try to call the same subroutine max with L1 part and recursively call the same subroutine max with L2 part. When both of these routine will return me a max value, I will just compare between the final two max values and I will return the first max as a maximum if the first max is greater than M2. Otherwise, I will return the second value that I get. In the earlier case, if you could see that during your search here, your recomposition step either takes a value from one part of the recursion tree that it called, or it takes another value from the other part. So the combination here, unlike your m square up to n square summation finding, it's just taking either one of the solutions and returning it as a compose step. Here it is taking both the solutions, just comparing but returning only one. The essence that I am trying to bring in here, your split can also differ, your compose step can also differ, and depending on your decomposition and recomposition steps, the efficiency also may matter. In the first case, we did not find such mattering with respect to split. Gradually, we will see example. Even in this case also, if you see that whether you split arbitrarily or in the middle or in one-sided tilted like 1 and n minus 1 size division, you will exactly have to compare n minus 1 number of times. The reason being that, you see, in your traditional or naive approach that you have followed to find max, what you do? You try to designate the first element as max. Then you try to compare the second element is greater than max or not. Then you re-update your max. In this way you proceed. So now see, after n minus 1 element you have scanned and found out your max. Then what you do? You try to compare with one element remaining, that is the nth element. So this is exactly splitting of your list into n minus 1 part and 1 part. What I am trying to say is that your recursive thinking in a generic sense will give you such special cases which you call as iterations in your algorithms, because Here n minus 1 and 1 split is nothing but traversing one after another each element, so you can implement it using iteration as well. However, even if you implement it using recursion by an arbitrary split or a middle split, you will exactly try to count the number of comparisons you are making. You will exactly see every time you need to do n minus 1 comparisons to get the maximum. So what does these two examples resemble? These two examples resembles that I am trying to devise efficient methods using recursion by the help of some jugglery in splitting and combining approaches. Now, anytime I could not go better than n minus 1 time comparison for finding max and n time comparisons for searching an element present in a list or not. Now, I leave it up to you to see that actually this problem cannot be solved without comparing n minus 1 times, or the search problem cannot be solved without comparing n times. The reason is very simple, because n minus 1 comparisons is required to find max due to the fact that you need to see all the elements at least once. And since two elements can be compared at most at a time, so therefore you need to compare n minus 1. You can prove it by contradiction that you must need n minus 1 time, because if you need less than n minus 1 time, you can contradict there are less elements than n that I could see to get the max. So therefore, what it points out is that the efficient strategy through recursions and through different mechanisms give me a number of comparisons which is actually the optimal number of comparisons. So I can say my algorithm is the best that I design, even if I do it recursively, splitting arbitrarily, even if I do it one-sided side list is 1 and the other side has n minus 1 nodes, both in case of searching an element and finding maximum. However, this is not an universal scenario that your split will always be not determining your solution betterness. We will try to see another example. Suppose instead of finding only the max, I give you a particular problem to find both max and minimum from a list of n elements. What will be your recursive formulations to this problem? So see, recursive formulations, as we are discussing, is nothing but providing these 4 steps. That is, what are the base cases, how we split, how we call, and how we compose and finally get back to the solution. So the base cases here, if your list has only one element, nothing to do, because that is the maximum, that is the minimum. Another base case is that if your list has 2 elements, then you need to compare between those 2 elements only and return the maximum, which one is the greater, and the minimum, which one is the lesser. So these 2 are my fundamental or the base cases where I can directly solve the problem. Let us again split it into arbitrarily 2 parts, n1 and n2. Then h1 is the max from the left part. I call h and l to denote as high and low, to signify like it's a max, it's a mean. h2 is another variable which I will just call the same subroutine from the right part and try to assign h2 from the max from there. Similarly, L1 is the minimum from the left part, L2 is the minimum from the right part. Now, recomposition step is that you compare between h1 and h2 to get the final maximum. You compare between L1 and L2 to get the final minimum. So here you can see that I need to have 2 comparisons each time to get the maximum and minimum. And in the base case, if n equal to 2, I need 1 comparison. If n equal to 1, I do not need any comparison. Now the point to ponder here, that here is the split really matters. Let us try to see the answer. Suppose you do it in your naive approach. How you solve this problem of finding max min? You just traverse the whole set of elements twice. Once you find the max, and that gets you n minus 1 number of comparisons. Again you traverse those n elements to find the mean in a similar way. That gives you another n minus 1 number of comparisons. As we have already studied, that these are the best way you can solve the max and mean separately. So actually the total number of comparisons you might need is 2n minus 2. Now check for some certain observations that might make your approach a little bit better before finding the best split strategy. In this approach, if you take two elements at a time when finding max, how would you proceed to do this? First two element I compare, found the max. Next two element I compare, find the max. In this way, I need to compare for the first level n by 2 number of pairs. Because there are n elements, I am comparing two elements at a time and trying to take the max out of them. So, after n by 2 number of comparisons, I get n by 4 number of candidates to compare again in the next level. Because n by 2 number of comparisons will give me n by 2 number of maximum element candidates after the first level of comparison. Then I go on comparing it with n by 4 number of times. Then again n by 8 number of times. So each time I eliminate half of the elements and go on comparing until I get the only one solution, that is my max. So if you add this GP series, you will exactly get n minus 1 comparisons. So therefore, that is the reason why I said that two elements are splitting in the middle also doesn't help only to find max. But here comes the smart observation when we are given to find max and mean together. See, at the first round, when you compare n by 2 pairs, that is 2 at a time, n elements. So n by 2 pair you compare. So you get a max between each pair. And there is one loser, right? When you compare 2 at a time, there is one winner and there is one loser. So each n by 2 pair will give you n by 2 number of losers. Now, there is no point of comparing between the winners to find the minimum, because winners will never get participated to find the minimum after first level, because there are losers which are less than each of them. So you only compare between n by 2 elements to find the minimum. Now see, your naive approach where you earlier traversed the list twice with n minus 1 comparison for finding max and mean reduces, because to find mean you need to only see n by 2 elements and need to have n by 2 minus 1 comparisons to do that. So you in total you get 3n by 2 minus 2 number of comparisons. Okay? So you get 3n by 2 minus 2 number of comparisons if you just have a smart observation. Now here you see that since finding max is nothing but looking at your recursion tree from a bottom up manner, isn't it? Because from n elements you pair up 2 at a time, then you pair up the max from the first level again 2 at a time and then compare. So now splitting really matters. If I get a middle split, if I have a middle split, then definitely I will get this kind of time comparison rather than naive one-sided one split and n minus 1 split. Because if I have 1 and n minus 1 split every time, then I have to compare twice with the result. See, this 1 can be max and mean both. From n minus 1 I get a max and a mean. So with this one element I need to compare twice. So this step will go n minus 1 time and each time I compare twice. So splitting with 1 and n minus 1 split will give you 2 into n minus 1. However, you check for a comparison if you split between 2 and n minus 2, because when you split two elements and try to find max and mean, you need one comparison due to this base case. This base case says you that if n equal to 2, you need one comparison to find the max and minimum. So, if your list is 2 with n minus 2, you need one comparison here. N minus 2 will give you another max and mean, and then you have to compare between max and mean of those two sets. If you go by this way, you will see that you will exactly get 3n by 2 minus 1 in case if it is even, and 3n by 2 minus 2 which we derive here in case if it is odd. You try with an example and see this will happen. Even if the middle split will give you 3n minus 3n by 2 minus 1 in the best way if it is even. So in a nutshell, what exactly we are cultivating here is how we can efficiently solve a problem by recursive thinking. That our naive solution is bad, so the splitting might matter. See the way I am trying to refine my problem and trying to get for a good solution. My naive solution is bad, so splitting might matter because I have a strategy to see my recursion tree in such a way, which we call the smart observation, that I could discard half of the elements and find mean and get a better number of comparisons. Therefore, 1 and n minus 1 split will not do. 2 and n minus 2 split is as good as the middle split because anyway I need to make it half and half. So that is the primary observation, and that is why I would try to tell you that before you jump into implementing something using recursion, try with pen and paper how these 4 steps comes in. What are your base cases? What are the way you could decompose? What are your recursive calls? How you recompose? Then finally try to twig in your splitting steps, your recomposition steps, because the total step that you will require is number of decomposition, number of recompositions and number of calls. That is your total time consumed of the total steps of this procedure. So therefore, if you could properly select such kind of options, you might get a better recursive strategy than you directly write it. So we come to a position where not only the recursion gives us a weapon to solve the problem, but also this recursive strategy makes our solution better and better if we think carefully. So that is why I try to give you some examples from this side so that you could build up strategies for recursive problem solving. Another problem which is of our importance and maybe a little bit tricky. So I will give you the strategy, but because once you get the strategy, then it is very easy to formulate the solution. So the problem goes that I need to generate all permutations of the string. For example, here say ABC, and the function that I will write is permute your array string, that array of characters which forms a string, and the initial index and the final index. Why I put initial and final index? Because I want to write a recursive function where this index position will matter as per my strategy. So now what I will try to do is that what is the recursive way of thinking this problem, that if my first letter is A and the rest of them I get all possible permutations, then I can combine that rest of all possible permutations with A and get my result. See the lowest two nodes in the left. A is already sit form in the first position. BC is one permutation of the rest thing. CB is another permutation of the rest things. So therefore, if I could concatenate A with each of these permutation, I will get a new permutation where those all are A sits in the front. Similarly, if my B sits in the front, then what about the rest? If I could permute, I will get all permutations where my B sits in the front. So on for each of the letters in the string or each of the alphabets in the string. So now see my strategy. My strategy goes that if I could somehow replace the first letter by each individual letters from the string and call recursively this subroutine for all other letters. So that is my decomposition phase. So my decomposition phase is nothing but swapping the first with the ith letter, my ith decomposition. For each A0 will be swapped with the first element, that means keeping A in the front. This second element can be swapped with the first, that means keeping B in the front, and the third element can be swapped with the first, keeping C in the front. And I call recursively for the rest n minus 1 length. So this way I could decompose, isn't it? Now, what will be my base cases? My base cases will be that whenever you reach upon, so in this way, the second level of recursive call where you are trying to permute between n minus 1 element set, again we'll try to swap the first position. First it will keep the first position as it is, then it will swap with the second element, third element and so on. So there will be a situation where there is only one element in the string. Then you just return that. because there is only one permutation possible, that is that character. So, what are the 4 steps that we find here? The base cases are your string has only one element, you directly return. If your string has more than one element, each element should be positioned at the first, so there should be a loop to position each element at the first position. For the rest of the elements, you just call the recursion, and then with the first element appending to a solution, you print it. So you first print A and the output that you get from this recursion. You print B followed by the output that you get from this recursion, and so on. Therefore, your recursive calls are, you swap each element with the ith, and when you swap each element with the ith, then up to that position you place and call by I plus 1 index to n. See here I do it in 3 length string. You can also try to see using 4 length string, but due to lack of space in this slide I put it in 3, but 4 length string would be much nice to notice. So I hope if you could see the way we split it, but here the splitting is not a constantly I am splitting once. It's a split happening in a loop, because each time I am trying to swap an element in the beginning and try to find for the rest. So splitting is one-sided is 1 and the other side is n minus 1, but it is happening n minus 1 number of times. That's why I need to find a loop where inside it sits the recursive calls. Unlike these steps, these algorithms where the recursive call is made only once, here the recursive call will be made in a loop. Okay. So just I want to point out that this is kind of a tricky recursion where you can generate all permutations of a string. You may also see that, so this is, you may also try to do yourself, if you can code this efficiently and can find out all permutations, then for an exercise you may also see all possible binary strings that you could make of n bits. You can also try to print all possible binary strings. Then also you can see that all possible power sets of a subset. All these things are efficient use of recursive techniques to solve this problem. So I hope you get a flavor of how we use recursions in our problem solving approach and how we can process that to find efficient and better solutions gradually. So with that, we come to an end of this topic of recursion, where we first discussed that how we recursively formulate. It just comes from your mathematical induction principle, but it goes top down in an approach. Then we try to figure out that how you can formulate a problem which could be solved in a better way in recursions, and there are problems where the sub problems that you recurse along are of the nature where they occur, the similar sub problems occur again and again. That's why in Fibonacci it is not good to recurse in a simpler way. There are ways to cater to those problems. So all of these we have seen in the previous lecture, and we have seen how the memory gets built up in an activation in terms of their activation records when we call a function and return from it. Today's lecture we saw that what are the fundamental ways in which we tackle a problem, and how do we find base cases, how do we find efficient strategies of splitting, that is decomposing and recomposing, and finally come to a solution which is one of the better solutions in terms of recursive problem solving. So thank you for your attention.